Have you ever wondered how your phone can just drop a virtual dinosaur right into your living room? Or how a self-driving car can possibly navigate a busy street? It all boils down to one huge question. How do computers see our world not as a flat picture, but in glorious 3D? Well, we're about to find out. I mean, it really seems like magic, doesn't it? The idea of taking a single, flat photo and somehow pulling out enough information to build a digital world you can actually move through. But it's not magic. It's this amazing mix of geometry and some serious computation. And we are going to pull back the curtain on how it's all done. So how in the world do we get from this, a simple, beautiful photo of a forest, to this? A sparse, yeah, but a spatially accurate 3D model made of thousands of tiny little points. This transformation, right here, is the absolute heart of computer vision. Okay, so to understand the solution, we first have to really appreciate the problem. And the biggest challenge, honestly, comes from the very nature of a photograph itself.
And yep, that problem has a name. It's called single-view ambiguity. See, when a three-dimensional world gets squashed down into a two-dimensional image, a really critical piece of information just vanishes: depth. Looking at a single picture, it is literally impossible to know for sure how far away anything is.
This slide shows that ambiguity perfectly with the famous Ames room illusion. Our brains and a computer would do the same thing, just assume the room is a normal rectangle. But as that diagram on the right shows, it's actually a trapezoid. This wrong assumption about the room's 3D shape is what tricks our eyes into seeing one person as a giant and the other as tiny. And come on, we've all seen or probably even taken photos just like these using forced perspective. Is that really a monster pumpkin, or is it just super close to the camera? Is that guy actually kicking the Leaning Tower of Pisa? Of course not. It just goes to show how easily a single 2D view can fool you about an object's real size and distance. So, if a single image is so ambiguous, how do we ever solve this puzzle? Well, the secret isn't just in the picture itself, it's in understanding the device that took it. Think of it this way. Every single camera, whether it's the one in your phone or one on the Mars rover, has a unique fingerprint. It's a set of characteristics that describes precisely how it turns the 3D world into a 2D image. If a computer can read this fingerprint, it can start to work backwards and figure things out. In the world of computer vision, this fingerprint is called the intrinsic matrix, or just the K-matrix for short. You can really just think of it as the camera's ID card. It holds all the critical inside info a computer needs to understand the geometry of any photo it takes. Now, I know this might look like a scary block of numbers, but the key parts are actually pretty simple. The most important values are the focal length, in this case 2000, which just tells us how zoomed in the lens is, and the principal point, at coordinates 960 by 540, which is the true center of the image sensor, kind of like the camera's bullseye. So we have the camera's ID card. Awesome. But to actually use it, computers need a special language to handle all the weird quirks of perspective. Think about train tracks stretching out into the distance. We know for a fact they're parallel, but in a photo, they look like they meet at a single point on the horizon. That vanishing point is, mathematically speaking, at infinity. Computers need a way to work with that idea, and that's where something called homogeneous coordinates comes in. So here's the comparison. A normal point is just a location, a spot. But a point at infinity isn't a place at all. It's a direction. And we represent this with a really clever trick. We just add a third coordinate. If that last number is a 0, the computer knows we're talking about a direction, like that vanishing point where the tracks meet, and not a specific spot. This lets one system handle both regular points and these infinite directions. Pretty neat, right? So now we have our two key ingredients: the camera's ID card, that K-matrix, and a mathematical language for dealing with perspective. Let's put them together and see how a 3D point becomes a 2D pixel. It's really just a simple 3-act story. First, we have an object somewhere in 3D space. Second, the camera, using its unique ID card, looks at that point. And third, through this mathematical process called projection, that 3D point lands on a very specific pixel on the 2D image sensor. Every single pixel in every photo you've ever taken is the result of this process. But of course, there's a little complication. The perfect pinhole camera model is a great starting point, but real-world lenses are made of curved glass. And this glass bends light just a little bit, creating this subtle warping, kind of like a fisheye effect, especially near the edges of a photo. This is called radial distortion. This slide shows exactly what's going on. An ideal grid would have perfectly straight lines, like you see on the left. But a real camera lens introduces these subtle curves, like on the right. What's absolutely amazing is that computers can model this exact distortion and then reverse it, creating a mathematically perfect image to work from. So how does a computer learn about its own lens distortion and all its other properties? It's through a process called calibration. And this isn't just some theory locked away in a lab, it's something anyone can do to find their own camera's secret ID card. The process is surprisingly simple. You just have your camera look at a pattern you already know, like a checkerboard, from a bunch of different angles. A simple program can easily find the corners of all the squares. And by analyzing how the perfectly straight lines of that checkerboard look all bent and warped in the photos, it can calculate the camera's unique intrinsic matrix, its secret ID card. And why does this one process matter so much? Because knowing the camera's exact geometry is the foundation for almost everything else in computer vision. To build an accurate 3D model, you need a calibrated camera. To place an augmented reality Pokémon convincingly in your living room, the software needs that camera's ID. For a self-driving car to judge how far away a pedestrian is, it relies on this calibration. It all starts right here. This flowchart basically shows the entire pipeline of modern computer vision. All the really exciting parts, like recognizing objects and building 3D worlds, are over on the right. But notice where it all begins, way over on the left with image formation. Everything we've just talked about, the camera's geometry, its ID card, the calibration, that is the foundation. It's the essential first step that lets us go from asking what is in a picture to truly understanding where it is in 3D space. So we've decoded the camera's secret ID card. That's the critical first step in allowing a machine to perceive depth. But this is really just the beginning of the journey from 2D to 3D. And the question that leaves us with is, what other secrets about our world are we going to unlock as computers continue to learn how to see?